Let's take another look at finding the volume of solids of revolution using the disk method. Earlier, we found the volume of the solid formed by rotating the region bound by both axes and the curve y equals 9 minus x squared rotated about the x-axis. First, let's take a quick look at the graph of the region. Y equals 9 minus x squared is a parabola with the y-intercept at 9, opens down, and has an x-intercept at 3. So here's a good look at our region, and if we rotate it about the x-axis, every point gets rotated around the x-axis, and so we'll have a shape that kind of looks like this, almost like a cone. Now we've been using this representative disk to help us set up our definite integral. Since our disk is vertical, the depth of this disk is delta x, and the radius is going to be that functional value at any point x over the interval. So that radius is going to be 9 minus x. In order to set up the integral, we remind ourselves that the volume of a disk is going to be pi r squared times its depth. So the volume of our region rotated about the x-axis is going to be the definite integral of pi r squared, where our radius is 9 minus x squared, and times the depth of our disk, which is dx, over the entire interval from the beginning to the end. Since everything is in terms of x, we're going to go from along the x-axis from 0 to 3. I won't take the time now to go through all the steps, but if you calculate this out, you should get 129.6 pi, which is 407.150. How does things change if we take the same region and instead of rotating it about the x-axis, we rotate it about the y-axis, meaning that this region will take every point and rotate it around the y-axis like so. So we'll end up with a shape like this. We're going to go through a very similar process where we're first going to need a representative disk. The only difference is that now our representative disk is horizontal, which means the depth of that disk is now a vertical distance, delta y, and our radius is a horizontal distance, which we need to have written in terms of y. Now we know that the function for this curve is y equals 9 minus x squared. When it's written like this, y is a vertical distance, and when we say y equals 9 minus x squared, we can represent that vertical distance in terms of x. But we don't want a vertical distance. Now we want a horizontal distance. I want to know what x is. So I need to take this equation and solve it for x. That's going to mean adding x to both sides and subtracting y, and then we take the square root. So x is going to be plus or minus the square root of 9 minus y. Now where we get the plus and minus from is that the right side of this curve, that's going to be the positive 9 minus y. The left side, that's going to be the negative root 9 minus y. Since I'm looking at things horizontally like this, I'm going to call that radius square root of 9 minus y. And now we have everything that we need to come up with our definite integral to find the volume. We remind ourselves that volume is pi r squared times height. So when we turn this into a definite integral, it's going to be pi times the radius, which our radius here is square root 9 minus y squared. And our height, or the depth of this disk, is going to be delta y, which in terms of the integral is dy. The only other thing we need are the limits of integration. Now remember, we're going to stack these disks vertically now, so we need to look at that interval in terms of y, is that vertical interval. So we're going to start at 0, but instead of going to 3, we're going to go up to 9. As we calculate this, it gets pretty nice. Pi is a coefficient which we can pull out in front. We'll take the integral from 0 to 9. Squaring the square root will leave us with 9 minus y dy. The integral of 9 minus y is 9y minus 1/2 y squared from 0 to 9. So when I plug in for 9, we'll have 81 minus 81 halves minus 0 minus 0 halves. So of course that's nothing. And it looks like this will end up being 81 halves pi. Or if you wanted to go 40.5 pi, that's going to end up being 127.234. A much smaller volume when we go around the y-axis than when we go around the x-axis. Let's try one more example. Find the volume of the solid form by rotating the region bound by y equals 3, x equals 0, and y equals e to the x rotated about the y-axis. The first thing that we should do is to graph what we're dealing with. When I graph it out, what I have in blue is our curve y equals e to the x. The horizontal line is y equals 3, and the line x equals 0 is going to be the y-axis. So here's our region that we're going to rotate around the y-axis. So every point on the curve is going to get spun around the y-axis like this. And so we'll end up with a shape kind of like this. We're going to set it up by using a horizontal representative disk. Since we're going to stack these things vertically, the depth of our disk is delta y, and our radius has to be a horizontal distance written in terms of y. So we're going to take our function y equals e to the x and solve it for x. Well, to get rid of e, we take the natural log of both sides, and we'll get that x is the natural log of y. So that means our radius is natural log of y. So let's set up our integral. The volume is going to be pi r squared, where our radius is natural log of y, and then the depth is dy. We need this definite integral to span over an interval. It's all in terms of y, so we want to see it go from here to here. On the top end, that's our green line, y equals 3. And on the bottom end, that's where y equals e to the x has its y-intercept, which is at 1. At this point, I'd go over to the calculator, calculate this out, and find the volume to be 3.233. But that's how you can find that volume when the region is rotated around the y-axis instead of the x-axis.